In this video, I want to talk about or go over an example of a degeneracy of states. Okay. So we're currently working on the eigenvalue problem, where if I have an operator and I act on a vector space, which I'm going to call omega I, then you get some factor omega I, which is a scalar, times that state again. So we operate with some operator omega. It operates on a particular vector space, and we get the exact same vector space back again right here. And all that's changed is now you have this multiplicative factor of a number multiplied by it, a scalar. So the example I want to talk about now is degeneracy, where we get two states with the same eigenvalue. So let's look at an example. And so the example, the operator that I want to consider is this 3 by 3 matrix of 1, 0, 1, 0, 2, 0, 1, 0, 1. Okay, so that's going to operate on our vector space. Now, the characteristic equation, if you remember, is the determinant of the operator minus the eigenvalue times the identity matrix, and we set that determinant equal to 0. So this determinant is going to be 1 minus the eigenvalue omega, 0, 1, 0, 2 minus the eigenvalue 0, 1, 0, 1 minus the eigenvalue, and that determinant is now equal to 0. So if we work out the determinant, what you get is from the first term 1 minus omega times the cofactor, which in this case would be 2 minus omega times 1 minus omega. So that's the first one. The second column doesn't give us, doesn't contribute to the determinant. The third column, that 1, will, and so that's plus 1 times the cofactor of the second and third columns, which would give us minus 1 times 2 minus omega. And all of that is set equal to 0. Okay, so if we work this out, then we get 1 minus omega squared times 2 minus omega minus 2 minus omega, which is equal to 0. You can factor out the 2 minus omega. So 2 minus omega, factored out, we have 1 minus omega quantity squared minus 1. Okay, so work it out a little further. We get 2 minus omega times 1 minus 2 omega plus omega squared minus 1, so is equal to 0. And if I still know my algebra, then I have omega squared minus 2 omega is equal to 0. I can factor out an omega, so I get omega 2 minus omega times omega minus 2 is equal to 0. And those last two parentheses are basically the same if I just factor out a minus sign. So you get minus omega, omega minus 2 times omega minus 2 is equal to 0. Or you can multiply both sides and get rid of the minus sign, and we're left with omega minus 2 squared is equal to 0. So basically, our three eigenvalues are going to be omega is equal to 0. And then since it's omega minus 2 squared, our two other eigenvalues are equal to 2. Okay, so the degeneracy means that two of our eigenvalues are the same value. So in this case, we have three eigenvalues because it's a 3 by 3 matrix operator that we're using. And one of the eigenvalues is 0, but two of the eigenvalues have the exact same value. So there's still three eigenvectors. We're still going to solve for three states. It's just that two of them now return the same eigenvalue, or in this case, the value of 2. Okay, so if we now go back and try and work out what the eigenvectors are, then what we would have is omega times the first eigenvector is equal to omega 1 times that first eigenvector. So in this case, what we would have basically is omega 1 is equal to 0, and we would end up with the let's see, the matrix omega minus omega 1 times the identity times the state is equal to the null. So in this case, what we would get is, if I look back at my matrix, 1 minus omega 1, 0, 1, 0, 2 minus omega 1, 0, 1, 0, 1 minus omega 1. Times the vector x1, x2, x3 is equal to the null, 0, 0, 0, like so. Okay, so in this case, omega 1 is 0, so we get 1, 0, 1, 0, 2, 0, 1, 0, 1, times x1, x2, x3 is equal to all zeros. Okay, so now if we multiply it out, you get x1 plus x3 is equal to 0. 2x2 is equal to 0. And x1 plus x3 is equal to 0. So that means that x2 is equal to 0. X1 is equal to minus x3. So if we just take, I don't know, a starting value of x1 equal to 1, and then we'll just normalize it later, our vector, omega 1, would be x1, 0 minus x1. Or factoring out the x1, 1, 0, minus 1. Like so. And if we then normalize it, we get x1, 1, 0, minus 1 over x1 times the square root of 1 squared plus minus 1 squared, or 1 over the square root of 2 times 1, 0, minus 1. So that's our first eigenvector. So now let's take a look at the case of the second eigenvector. So for the second eigenvector, so now omega 2 is equal to 2. We could write out the matrix equation again. 1 minus 2, 0, 1, 0, 2 minus 2, 0, 1, 0, 1 minus 2, times x1, x2, x3 is equal to the null, 0, 0, 0. like so. And so what we get is -1, 0, 1, 0, 0, 0, 1, 0, -1 times x1, x2, x3, and that's equal to 0, 0, 0. Okay, so our three linear equations become minus x1 plus x3 is equal to 0. 0 is equal to 0. So x2 doesn't seem to contribute at all. And x1 minus x3 is equal to 0. So what does that mean? Well, that means that x1 is going to be equal to x3, and x2 is arbitrary. It doesn't matter what the value of x2 is going to be. Okay, so let's write out the vector. So that means we have our second vector is now x1, I'm sorry, 1, x2 is arbitrary, and then I have basically x1. So if I factor out the x1, then I get 1 x2 divided by x1 and a 1. So again, we can kind of set, the x1 is going to drop out in the normalization, but we can set x2 divided by x1, which is basically, arbitrary. The x2 value doesn't really play into the solution, so I'm going to set that equal to 1. And so when we normalize it, what we get is x1 over 1, 1, 1 divided by x1, the square root of 1 squared plus 1 squared plus 1 squared, which gives me 1 divided by the square root of 3, 1, 1, 1. Okay. So that's our second eigenvector. Okay, so we've now found two of the eigenvectors. The one that corresponds to the eigenvalue omega 1, and the other one which corresponds to the eigenvalue of omega 2. So now for omega 3, it has the same eigenvalue as omega 2. Both of them are equal to 2. So it's hard to distinguish between the value that's in x, the omega 2 and omega 3. But it turns out that basically omega 3 has to be orthogonal to both omega 1 and omega 2. And so the solution that you get for omega 3 is 1 over the square root of 6 times 1 minus 2, 1. If we're to ensure that third eigenvector is going to be orthogonal to the other two. So in the end, you can kind of write this down now as our first eigenvector, where is the eigenvalue of 0, a second eigenvector, which is an eigenvalue of 2, which we can put comma the first one, and then we get a third eigenvector, which has a eigenvalue of 2, which is the second one, our degenerate state.